Hidden behind the sun's glare for months, a 22,000-year wanderer is returning home. But what if SWAN R2 isn't just a harmless visitor? A comet the size of a mountain, traveling for over 2 decades of millennia, suddenly develops an unstable orbit. What if it doesn't peacefully pass by Earth as predicted? What if something goes catastrophically wrong? SWAN R2 carries more than just ancient ice and dust. It holds the potential for scenarios that could reshape our world forever. A slight gravitational nudge from Jupiter, an unexpected fragmentation event, a debris field crossing Earth's path at the worst possible moment. Tonight, as you drift into sleep, we'll explore the darkest possibilities lurking within this celestial visitor's journey. From asteroid impacts that changed history to the physics of cosmic destruction, we'll examine what happens when nature's most beautiful phenomena become harbingers of catastrophe. The odds are astronomical. The consequences would be unthinkable. But in space, even the most unlikely scenarios demand our attention. Subscribe to explore the universe's most terrifying what-if scenarios. There's something haunting about the way comets move through space. Silent harbingers carrying the potential for both wonder and devastation. As SWAN R2 makes its spectacular return after 22,554 years in the outer darkness, we must confront an uncomfortable truth. Even the most beautiful celestial visitors can become agents of catastrophic change. SWAN R2 announced its presence to our solar system like a ghost materializing from the cosmic void. Hidden for months behind the sun's overwhelming glare, this ancient wanderer remained invisible to our most powerful telescopes until September 11, 2025, when Vladimir Bezugli detected its characteristic hydrogen signature in SWAN instrument data. The timing was almost miraculous, or perhaps ominous. Just one day after discovery, the comet reached perihelion, the closest point in its 22,000-year orbit around our Sun. What emerged from the solar glare was magnificent and terrifying in equal measure. SWAN R2 sported a tail stretching 2.5 degrees across the sky, equivalent to 5 full moon diameters lined up in a row. For observers in the southern hemisphere, it became a spectacular sight through binoculars, its greenish coma and sweeping tail painting a celestial portrait that hadn't been seen since our ancestors were developing agriculture. But beneath this beauty lurks a more sobering reality. SWAN R2 is massive, potentially several kilometers across, with a mass measured in trillions of kilograms. It's traveling at velocities that transform even the smallest fragments into city-destroying projectiles. As it approaches Earth's orbital neighborhood in October 2025, coming within 39 million kilometers of our planet, we're reminded that the line between cosmic spectacle and existential threat can be terrifyingly thin. The comet's origins in the Oort cloud make its behavior inherently unpredictable. Objects from this distant realm have spent eons in the deep freeze of space, their internal structure potentially weakened by cosmic radiation and thermal stress. When they venture close to the sun's heat after millennia of dormancy, they can behave in ways that defy our models and expectations. Consider the case of Comet Ison in 2013, which was expected to become one of the most spectacular comets in history. Instead, it disintegrated as it approached the sun, breaking apart into a cloud of debris that posed new and unexpected risks. Or Comet Shoemaker Levy 9, which fragmented into multiple pieces before crashing into Jupiter in 1994, each impact releasing energy equivalent to millions of nuclear weapons. SWAN R2's 22,000-year orbital period means we have no historical precedent for how this specific object behaves under solar heating. The last time it visited the inner solar system, Human civilization consisted of small hunter-gatherer groups. We have no records, no observations, no data about its previous behavior during perihelion passage. What we do know is troubling. Long-period comets like SWAN R2 are particularly prone to outbursts, sudden, violent releases of gas and dust that can dramatically alter their trajectories. These outbursts occur when pockets of highly volatile materials, perhaps carbon monoxide or methane that has remained frozen for millennia, suddenly vaporize under solar heating. The resulting jet of material acts like a rocket engine, potentially nudging the comet onto a slightly different path. For an object passing relatively close to Earth, even a small change in trajectory could have profound consequences. Computer simulations show that an outburst occurring at the wrong time could shift SWAN R2's closest approach distance by hundreds of thousands of kilometers, the difference between a harmless flyby and a potentially catastrophic encounter. The gravitational environment SWAN R2 is entering compounds these risks. As the comet approaches the inner solar system, it must navigate the gravitational influences of Jupiter, Mars, and Earth. These planetary perturbations, while normally predictable, become dangerous wildcards when combined with the unpredictable non-gravitational forces generated by cometary outgassing. Jupiter, in particular, poses both protection and threat. The giant planet's immense gravity has historically acted as a cosmic vacuum cleaner, capturing or deflecting many potentially dangerous objects before they can reach the inner solar system. But Jupiter can also act as a gravitational slingshot, accelerating objects to even higher velocities or redirecting them onto more dangerous trajectories. The timing of SWAN R2's approach relative to planetary positions adds another layer of complexity. The comet's closest approach to Earth on October 19, 2025, occurs when our planet is in a specific position in its orbit. Small changes in the comet's trajectory could cause it to arrive when Earth is in a different position, potentially creating encounter scenarios that weren't accounted for in initial risk assessments. Perhaps most concerning is what we don't know about SWAN R2's internal structure. Ground-based observations can tell us about the comet's size, composition, and activity level, but they reveal little about its structural integrity. Is it a solid, monolithic object that will remain intact throughout its passage? Or is it a loose collection of fragments held together by little more than weak gravity and ice, a rubble pile that could break apart at any moment? The distinction matters enormously. A solid comet that maintains its integrity poses one type of risk, but a fragmenting comet creates multiple threats moving on slightly different trajectories, turning a single predictable object into a swarm of unpredictable projectiles. History provides sobering examples of how quickly cosmic situations can deteriorate. In 1908, a much smaller object, possibly a fragment of a comet or asteroid just tens of meters across, exploded over the Tunguska region of Siberia with the force of 1,000 Hiroshima bombs flattening forests across 2,000 square kilometers. SWAN R2 contains millions of times more mass than the Tunguska impactor. The Chicxulub impact 66 million years ago, which contributed to the extinction of the dinosaurs, involved an object perhaps 10-15 kilometers across, similar in size to SWAN R2's estimated dimensions. While our comet's current trajectory poses no direct impact threat, the physics of such encounters remind us of the devastating potential locked within these ancient wanderers. As SWAN R2 continues its approach through the inner solar system, astronomers around the world maintain constant vigilance, tracking its position and behavior for any signs of unexpected activity. But even with our most sophisticated monitoring systems, we're essentially watching a cosmic wildcard whose behavior could change without warning. The beautiful tale streaming behind SWAN R2 as it approaches the Sun, isn't just a spectacular light show. It's visible evidence of the comet's ongoing transformation under solar heating. Every day, millions of tons of material stream away from its nucleus, potentially altering its mass distribution and rotational characteristics in ways that could affect its future trajectory. In the coming weeks, as SWAN R2 makes its closest approach to both Earth and the Sun, we'll have our best opportunity to study this ancient visitor and assess the full scope of both its beauty and its potential for destruction. But even as we marvel at its spectacular display, we must remember that in the cosmic arena, even the most breathtaking performances can quickly become something far more sinister. The worst-case scenarios we'll explore tonight aren't science fiction. They're mathematical possibilities embedded in the complex dance of gravitational forces and cosmic chance that governs our solar system. Throughout Earth's 4.6 billion-year history, our planet has been repeatedly reminded that space is not the peaceful void it appears to be. The geological record tells a story written in craters and extinction events, each chapter marking a moment when the cosmos reached down to fundamentally alter the course of life on Earth. As we watch SWAN R2's approach, we must remember that comets and their rocky cousins have been agents of both creation and destruction since the dawn of our world. The most famous of these cosmic catastrophes occurred 66 million years ago, when an object roughly 10 to 15 kilometers across, similar in size to SWAN R2, slammed into what is now the Yucatan Peninsula of Mexico. The Chicxulub impact released energy equivalent to billions of nuclear weapons, instantly vaporizing rock and creating a crater 150 kilometers wide. But the immediate destruction was only the beginning of a global catastrophe that would reshape life on Earth forever. The impact sent shockwaves through the Earth's crust, triggering massive earthquakes and volcanic eruptions around the globe. A plume of superheated rock and debris was blasted into space, raining back down as glowing projectiles that turned the sky into a furnace. Forests worldwide burst into flames as the atmosphere itself became an oven. But perhaps the most devastating effect was the impact winter that followed. The collision threw so much dust and debris into the atmosphere that sunlight was blocked for months, possibly years. Global temperatures plummeted. Photosynthesis virtually ceased as plants died en masse. The food chain collapsed from the bottom up, leading to the extinction of roughly 75% of all species on Earth, including the non-avian dinosaurs that had dominated the planet for over 160 million years. This wasn't an isolated event. The geological record reveals at least 5 major extinction events in Earth's history, several of which may have been caused or triggered by cosmic impacts. The Permian-Triassic extinction 252 million years ago, the most severe biodiversity crisis in Earth's history, eliminated over 90% of marine species and 70% of terrestrial vertebrates. While volcanism likely played the primary role, some scientists suspect that one or more impact events may have been the catalyst that pushed Earth's climate system past a catastrophic tipping point. More recently, we've witnessed the sobering reality of how quickly cosmic threats can materialize. On February 15, 2013, the Chelyabinsk meteor exploded over Russia with the force of about 30 Hiroshima bombs. The object was only about 20 meters across, a tiny fragment compared to SWAN R2, yet its airburst shattered windows across 6 cities, injured over 1,500 people, and served as a wake-up call about our vulnerability to cosmic projectiles. What made the Chelyabinsk event particularly unsettling was that it caught astronomers completely by surprise. Despite our extensive sky surveys and asteroid monitoring programs, this potentially devastating object remained undetected until the moment it began burning up in our atmosphere. It approached from the direction of the sun, hidden in the solar glare. eerily similar to how SWAN R2 remained concealed for months before its discovery. The Tunguska event of 1908 demonstrated how even a modest cosmic visitor can unleash continental-scale destruction. An object perhaps 60 meters across, likely a fragment of a comet or asteroid, exploded about 8 kilometers above the Siberian forest, with an estimated energy of 10-15 megatons. The blast flattened trees across 2,000 square kilometers, killing every living thing in the immediate area and generating seismic waves detected around the world. Had the Tunguska object arrived just a few hours later, Earth's rotation would have carried St. Petersburg or London directly beneath its path. Instead of devastating an uninhabited forest, it would have obliterated one of Europe's major cities, killing hundreds of thousands and potentially altering the course of history on the eve of World War I. These historical events illustrate a crucial point about cosmic catastrophes. They're not gradual processes that unfold over decades or centuries. They happen in an instant, with little or no warning, transforming a normal day into a defining moment in planetary history. The object that created the Chicxulub crater was probably visible to any hypothetical observers for only the last few seconds before impact. A bright point of light growing rapidly larger until it filled the sky and changed everything forever. Comets present unique challenges compared to asteroids because of their inherently unstable nature. While rocky asteroids follow predictable paths governed primarily by gravitational forces, comets are subject to non-gravitational perturbations caused by the outgassing of volatile materials as they heat up near the sun. These jets of vaporizing ice can act like tiny rocket engines, subtly altering the comet's trajectory in ways that are difficult to predict. Comet Swift-Tuttle, which produces the annual Perseid meteor shower, provides a sobering example of how cometary orbits can shift over time. This massive object, roughly 26 kilometers across, follows an orbit that brings it relatively close to Earth every 133 years. Calculations show that gravitational perturbations could potentially alter its orbit enough to create a collision course with our planet, sometime in the distant future. While the risk is extremely low, the fact that it exists at all demonstrates the long-term instability inherent in cometary orbits. The fragmentation of comets adds another layer of complexity to impact scenarios. Comet Shoemaker-Levy. 9's breakup and subsequent collision with Jupiter in 1994 provided astronomers with a spectacular demonstration of what happens when a large comet disintegrates. The fragments, ranging in size from a few hundred meters to several kilometers across, struck Jupiter over the course of several days, each impact creating fireballs larger than Earth and leaving dark scars in the planet's atmosphere that persisted for months. If a similar fragmentation event occurred with an Earth-approaching comet like SWAN R2, the results could be catastrophic. Instead of a single large impact, our planet could face a sustained bombardment lasting days or weeks. Even if individual fragments were too small to cause global extinction, the cumulative effects of multiple regional impacts could devastate civilization and cause widespread ecological collapse. The 1994 collision with Jupiter also revealed the immense energies involved in cometary impacts. Each of Shoemaker-Levy 9's larger fragments released energy equivalent to millions of nuclear weapons, far exceeding the destructive power of humanity's entire nuclear arsenal. The largest fragment, estimated to be about 2 kilometers across, created an explosion visible from Earth, despite occurring on the far side of Jupiter. Modern computer simulations of large impact events paint an increasingly detailed picture of how such catastrophes unfold. For an object the size of SWAN R2, the immediate effects would include the complete destruction of everything within hundreds of kilometers of the impact site. The blast wave would level buildings and forests across continental distances. Mega tsunamis hundreds of meters high would scour coastlines if the impact occurred in an ocean. But the global effects would be even more devastating. The impact would inject enormous quantities of dust and debris into the stratosphere, blocking sunlight and causing global temperatures to plummet. Agricultural systems would collapse as crops failed worldwide. The resulting famine could kill more people than the initial impact itself. Volcanic activity triggered by the impact could compound the crisis, releasing additional ash and gases into the atmosphere. Some models suggest that very large impacts could trigger massive volcanic eruptions on the opposite side of the planet, as seismic waves focus and amplify at the antipodal point. Perhaps most disturbing is the realization that even our advanced technological civilization would be largely helpless against such an event. While we've developed the ability to detect and track many potentially hazardous objects, our capacity to deflect or destroy them remains extremely limited. For an object the size of SWAN R2, discovered only months before a potential impact, there would be little we could do except watch and prepare for the aftermath. The historical record makes it clear that large impact events are not just possible. They are inevitable on geological timescales. The question isn't whether Earth will face another major cosmic collision, but when. As we monitor SWAN R2's approach and contemplate the worst-case scenarios, we're forced to confront the uncomfortable reality that our planet exists in a cosmic shooting gallery where the next shot could come at any time. But what specific mechanisms could transform SWAN R2 from a beautiful celestial visitor into an agent of global catastrophe? To understand the true scope of the threat, we must examine the physics of orbital mechanics and the delicate gravitational dance that determines the fate of every object in our solar system. In the cosmic arena, the difference between a harmless celestial show and global catastrophe often comes down to a matter of meters per second, tiny velocity changes that can accumulate over time into dramatically different orbital outcomes. As SWAN R2 navigates the gravitational maze of our inner solar system, it's dancing on the edge of chaos theory, where microscopic changes in initial conditions can lead to vastly different results. To understand how a comet like SWAN R2 could transform from a benign visitor into an existential threat, we must first grasp the fundamental principles governing its motion through space. The comet is essentially a massive projectile following a precisely determined path through the gravitational fields of the Sun, planets, and countless smaller bodies. Under normal circumstances, these gravitational influences are predictable, allowing astronomers to calculate its trajectory with remarkable precision. But SWAN R2 is not a simple gravitational projectile like an asteroid. As it approaches the Sun and begins to heat up, volatile materials in its nucleus start to vaporize and stream away into space, creating the spectacular tail we observe, but also generating what astronomers call non-gravitational forces. These jets of escaping gas act like tiny rocket engines, capable of nudging the comet's velocity by fractions of a meter per second. Such small changes might seem insignificant, but in the precisely choreographed dance of orbital mechanics, even tiny perturbations can have profound consequences. A velocity change of just 1 meter per second, applied at the right time and direction, could alter SWAN R2's closest approach distance to Earth by thousands of kilometers. Over longer timescales, such changes can completely reshape an object's orbit, transforming it from a safe periodic visitor into a potentially hazardous Earth-crosser. The physics becomes even more complex when we consider the three-body problem, the gravitational interaction between SWAN R2, the Sun, and Earth. While the two-body problem, just the comet and Sun, has elegant mathematical solutions, adding a third massive object like Earth creates a system that can exhibit chaotic behavior. Small changes in the comet's position or velocity can lead to dramatically different outcomes as it navigates through regions of gravitational resonance and instability. Jupiter's gravitational influence adds another layer of complexity to this already chaotic system. The giant planet's immense mass, more than twice that of all other planets combined, creates gravitational perturbations that can be felt throughout the solar system. For objects in highly elliptical orbits like SWAN R2, encounters with Jupiter's gravitational field can act like cosmic billiard ball collisions, dramatically altering velocities and trajectories. Computer simulations of long-period comets reveal a sobering truth. Their orbits are inherently unstable over long time scales. While SWAN R2's current trajectory appears safe, modeling its future evolution over multiple orbital periods shows a range of possible outcomes, some of which include close encounters or even collisions with Earth. The probability of any single catastrophic scenario may be low, but the cumulative risk over thousands of orbital periods becomes significant. The concept of gravitational resonance plays a crucial role in understanding how seemingly stable orbits can suddenly become dangerous. When a comet's orbital period maintains a simple mathematical relationship with a planet's orbital period, such as 2.1 or 3.2 ratios, the repeated gravitational tugs can either stabilize the orbit or drive it toward chaos. SWAN R2's 22,554-year orbital period potentially places it near resonances with several planets, creating zones of orbital instability that could be triggered by relatively small perturbations. One of the most concerning scenarios involves what astronomers call orbital resonance capture. If SWAN R2's orbit evolves to achieve a precise resonance with Jupiter or another planet, the repeated gravitational interactions could gradually pump energy into the comet's orbit, potentially increasing its eccentricity or inclination in ways that bring it dangerously close to Earth's orbital path. The fragmentation scenarios present perhaps the most complex and unpredictable physics. When a comet breaks apart, the resulting fragments follow slightly different trajectories determined by their individual masses, shapes, and the velocity imparted during the breakup event. These fragments can spread out over time, creating a debris stream that may intersect Earth's orbit at multiple points. The physics of cometary fragmentation involves a complex interplay of thermal stress, rotational forces, and internal structural weaknesses. As SWAN R2 approaches the Sun, differential heating creates thermal gradients within its nucleus. Materials on the sunward side expand, while those in shadow remain cold and contracted, creating internal stresses that can exceed the comet's structural limits. Rotational breakup represents another fragmentation mechanism. As volatile materials vaporize and escape from specific regions of the nucleus, they create torques that can spin up the comet's rotation. If the rotation rate exceeds the comet's gravitational binding limit, typically just a few hours for objects this size, centrifugal forces can literally tear it apart. The timing of any fragmentation event is crucial in determining the threat level. A breakup occurring near aphelion, the comet's farthest point from the Sun, would spread the fragments over a relatively large volume of space, reducing the probability of Earth encounters. But fragmentation near perihelion, when the comet is moving at its highest velocity and closest to the inner solar system, could create a concentrated debris stream that poses a more immediate threat. Chaos theory tells us that certain regions of phase space, combinations of position and velocity, are inherently unstable, leading to exponential divergence of initially similar trajectories. For comets like SWAN R2, these chaotic zones often occur near close approaches to massive planets or at specific orbital resonances. A comet entering one of these zones might follow a relatively predictable path for decades or centuries before suddenly diverging onto a radically different trajectory. The mathematical tools for predicting chaotic behavior have their limits. While we can identify regions of potential instability and calculate probability distributions for various outcomes, the precise timing and nature of chaotic transitions remain fundamentally unpredictable. This inherent uncertainty means that even our most sophisticated computer models cannot definitively rule out catastrophic scenarios, no matter how improbable they might seem. Modern astrodynamics employs Monte Carlo methods to explore the range of possible futures for objects like SWAN R2. These simulations run thousands or millions of slightly different scenarios, varying the initial conditions within observational uncertainties to map out the probability space of potential outcomes. While most simulations show safe passages, a small percentage inevitably includes scenarios where gravitational perturbations or outgassing events redirect the comet onto dangerous trajectories. The gravitational environment of the inner solar system contains several known hazardous regions where small velocity changes can have outsized effects. The Earth-Moon system's gravitational field creates a complex web of stable and unstable regions, including the Earth's Hill sphere, the region where our planet's gravity dominates over the Sun's. Objects passing through this region can experience dramatic orbital changes depending on their exact trajectory and timing. Lagrange points, locations where the gravitational forces of two massive bodies balance, represent another source of orbital instability. While these points can trap objects in stable configurations for long periods, they can also act as gravitational launch pads that accelerate objects onto new trajectories when perturbed by outside forces. The phenomenon of gravitational focusing adds another dangerous element to close planetary encounters. When a comet approaches a massive object like Earth, the planet's gravity effectively focuses the trajectory, increasing the probability of impact beyond what would be expected from simple geometric considerations. This effect becomes more pronounced for slower-moving objects, potentially making fragments of a disrupted comet more dangerous than the original intact nucleus. Recent research has revealed that the gravitational effects of seemingly minor bodies can accumulate over long timescales to produce significant orbital changes. The combined gravitational influence of asteroids, comets, and even dust particles can create what scientists call orbital friction, a gradual evolution of orbits that can move objects into or out of dangerous resonances over millions of years. Perhaps most unsettling is the realization that our current understanding of these complex gravitational interactions remains incomplete. New phenomena are still being discovered as our computational capabilities improve and our observational data becomes more precise. As we track SWAN R2's current approach, astronomers are not just observing a beautiful comet. They're monitoring a complex dynamical system poised on the edge of chaos, where the slightest perturbation could initiate a cascade of events leading to outcomes we can barely imagine. The physics of catastrophe operates on scales both vast and intimate, reminding us that in the cosmos, even the most minute changes can have consequences that reshape worlds. But understanding the physics is only the beginning. To truly comprehend the threat that objects like SWAN R2 might pose, we must examine the specific mechanisms by which a distant comet could find itself on a collision course with our planet. In the precise clockwork of celestial mechanics, the difference between a safe passage and planetary catastrophe can be measured in degrees of arc smaller than the apparent width of a human hair held at arm's length. As SWAN R2 continues its approach toward Earth's orbital neighborhood, we must confront the uncomfortable reality that several plausible scenarios could redirect this ancient wanderer onto a collision course with our planet. The current trajectory calculations show SWAN R2 passing safely by Earth at a distance of approximately 39 million kilometers on October 19, 2025. This might seem like a comfortable margin, roughly 100 times the distance to the Moon. But in cosmic terms, it represents a relatively close encounter that places the comet well within the gravitational sphere of influence, where small perturbations can have large consequences. To understand how SWAN R2 could potentially threaten Earth, we must first examine the concept of orbital evolution. Unlike the stable, nearly circular orbits of planets, comets follow highly elliptical paths that make them exquisitely sensitive to gravitational perturbations. Each time SWAN R2 approaches the inner solar system, it runs a gravitational gauntlet of planetary influences that can subtly reshape its orbit. The most immediate concern involves outgassing-induced trajectory changes during the comet's current passage. As SWAN R2 heats up near the Sun, jets of vaporizing ice create thrust vectors that act like a natural propulsion system. These jets are not uniformly distributed around the nucleus. They tend to be concentrated on the Sun-facing hemisphere and can vary in intensity as different volatile materials reach their sublimation temperatures. Computer models suggest that an asymmetric outburst occurring at a critical point in SWAN R2's orbit could alter its velocity by several meters per second. This might not sound significant, but applied at perihelion, when the comet is moving at its highest speed and closest to the Sun, such a velocity change could shift the comet's aphelion by millions of kilometers, potentially bringing its future orbit closer to Earth's path. The timing of such an outburst is crucial. If a major outgassing event occurs when SWAN R2 is positioned so that the thrust vector has a component in the direction of orbital motion, it could increase the comet's orbital energy, expanding its orbit and potentially extending its orbital period. Conversely, a thrust vector opposing orbital motion could shrink the orbit, reducing the period and bringing the comet back sooner than expected. More ominously, a thrust vector applied perpendicular to the orbital plane could change the comet's inclination, potentially causing future orbits to intersect Earth's path at different angles. Such inclination changes are particularly dangerous because they can create high-velocity encounter geometries where the relative speed between the comet and Earth approaches 60–70 kilometers per second. Jupiter's gravitational influence presents another pathway by which SWAN R2 could evolve into an Earth-threatening object. While the giant planet is often called Earth's protector because it captures or deflects many potentially dangerous objects, it can also act as a gravitational slingshot that accelerates comets to higher velocities or redirects them onto more dangerous trajectories. The key lies in the geometry of gravitational encounters. A comet approaching Jupiter from certain angles can receive a gravity assist that dramatically increases its velocity and expands its orbit. If SWAN R2's orbit evolves over multiple passages to create such an encounter geometry with Jupiter, the resulting velocity change could transform it from a long-period comet into a Jupiter family comet with a much shorter orbital period and potentially dangerous Earth-crossing trajectory. The Tisserand parameter, a mathematical quantity that remains approximately constant during gravitational encounters, provides insight into how Jupiter encounters can reshape comet orbits. Objects with Tisserand parameters near specific values are particularly susceptible to dramatic orbital changes during close approaches to Jupiter, potentially shifting from safe heliocentric orbits to Earth-threatening trajectories. Resonance capture represents another mechanism by which SWAN R2 could gradually evolve onto a dangerous path. If the comet's orbital period drifts into a simple ratio with Earth's orbital period, such as 2.132 or 5.3, the repeated gravitational tugs from our planet could gradually pump energy into the comet's orbit through a process called secular resonance. The most dangerous scenario involves capture into the 1.1 resonance, where the comet's orbital period exactly matches Earth's. This configuration, similar to that of asteroids in Earth's Trojan points, could gradually reduce the orbital eccentricity through tidal forces, eventually bringing the comet's entire orbit within Earth's vicinity. While this process typically takes millions of years, It demonstrates how seemingly safe orbits can evolve into threatening configurations. Fragmentation scenarios add another layer of complexity to impact probability calculations. If SWAN R2 breaks apart during its current passage, the resulting fragments would follow slightly different trajectories based on their individual masses and the velocities imparted during the breakup event. Some fragments might be deflected onto more dangerous orbits, while others are scattered into safer trajectories. The most concerning fragmentation scenario involves a breakup occurring near perihelion, when the comet is moving at maximum velocity and closest to the gravitational influences of the inner planets. Fragments created at this point would have the highest probability of evolving onto Earth-crossing orbits during subsequent passages around the Sun. Observational uncertainties in SWAN R2's current trajectory introduce additional elements of unpredictability. While astronomers have determined the comet's orbit with impressive precision, small measurement errors accumulate over time through a process called orbital uncertainty propagation. These uncertainties create a probability cloud of possible future positions that grows larger with each orbital period. Current estimates suggest that after just one complete orbit, 22,554 years, the uncertainty in SWAN R2's position could span millions of kilometers. Over multiple orbital periods, this uncertainty envelope could encompass Earth's entire orbital path, making long-term predictions of collision probability extremely difficult. The Yarkovsky effect, though typically associated with smaller asteroids, could also influence SWAN R2's long-term orbital evolution. This phenomenon occurs when asymmetric thermal emission from a rotating object creates a small but persistent thrust. For a comet like SWAN R2, differential heating and cooling as it rotates could gradually alter its orbit over thousands of years. Modern impact probability calculations employ sophisticated Monte Carlo methods that run millions of simulations with slightly different initial conditions to map out the space of possible futures. These calculations consistently show that while the probability of SWAN R2 directly threatening Earth during its current passage is extremely low, the cumulative risk over multiple orbital periods is more significant. One particularly sobering result from these simulations involves close approach scenarios where SWAN R2 passes within the Moon's orbital distance. Such encounters, while rare, could subject the comet to powerful tidal forces from Earth's gravity that might trigger fragmentation or significant orbital changes. The resulting debris stream could pose risks for decades or centuries, as individual fragments follow their own chaotic trajectories. The gravitational keyhole concept, first developed for asteroid 999942 Apophis, applies equally to comets like SWAN R2. These are narrow regions of space where a gravitational encounter could precisely redirect an object onto a collision course with Earth during a subsequent orbit. For SWAN R2, such keyholes might exist near its closest approach point, representing zones where seemingly minor trajectory changes could have catastrophic long-term consequences. Climate change and Earth's evolving gravitational field add another variable to long-term impact calculations. As ice caps melt and mass redistributes across Earth's surface, our planet's gravitational field undergoes subtle changes that could influence the trajectories of close-approaching objects over geological timescales. The discovery of additional small bodies in the outer solar system has revealed that our understanding of gravitational perturbations remains incomplete. Unknown dwarf planets or large asteroids in the outer reaches could exert cumulative gravitational influences that gradually alter the orbits of long-period comets like SWAN R2 in ways we cannot currently predict. Perhaps most unsettling is the realization that some orbital evolution scenarios operate on timescales comparable to the stability of human civilization itself. A trajectory change that begins during SWAN R2's current passage might not manifest as an Earth-threatening configuration for thousands of years, creating a delayed-action cosmic time bomb that future generations would be powerless to prevent. The mathematical tools available to modern astronomers can identify many possible pathways by which SWAN R2 could evolve from its current safe trajectory into an Earth-threatening orbit. While the probability of any specific catastrophic scenario remains low, the existence of multiple plausible mechanisms reminds us that the line between cosmic spectacle and existential threat is often determined by factors beyond our current ability to predict or control. As we continue to monitor SWAN R2's passage through our cosmic neighborhood, we're not just tracking a beautiful comet. We're observing a potentially dangerous object whose future behavior could be shaped by forces and interactions we're only beginning to understand. The orbital mechanics of doom operate according to the same physical laws that govern the benign motions of planets and moons, reminding us that, in the universe, beauty and danger often travel hand in hand. But even if SWAN R2 maintains its current safe trajectory, its passage raises important questions about our preparedness for cosmic threats and the measures we might take to detect and defend against future visitors that might not be so benign. There's something deeply unsettling about watching a mountain-sized object tear itself apart in the silence of space. When Comet Shoemaker Levy 9 fragmented in 1992, astronomers witnessed a preview of cosmic destruction that forever changed our understanding of how quickly a single threat can multiply into a sustained bombardment. As SWAN R2 approaches the intense thermal environment near the Sun, the possibility of a similar fragmentation event transforms our worst-case scenarios from a single catastrophic impact to something far more complex and dangerous. The physics of cometary fragmentation operates on principles that seem almost designed to maximize chaos. Unlike rocky asteroids, which are held together by strong molecular bonds in solid minerals, comets are essentially dirty snowballs. Loose aggregations of ice, dust, and rocky debris bound together by little more than their own weak gravity and the frozen ices that act as cosmic cement. When these ancient objects venture close to the Sun after millennia in the deep freeze, they undergo dramatic thermal stress that can exceed their structural limits in a matter of hours or days. SWAN R2's journey from the outer solar system to perihelion represents one of the most extreme environmental transitions possible in our cosmic neighborhood. For over 20,000 years, this comet has existed at temperatures just a few degrees above absolute zero, where even carbon dioxide remains solid. Now, as it approaches within 75 million kilometers of the Sun, its surface temperature could rise to hundreds of degrees Celsius within a matter of weeks. This rapid heating creates differential thermal expansion throughout the nucleus. The Sun-facing hemisphere begins to expand as ices sublimate and rocky materials heat up, while the shadowed regions remain cold and contracted. These thermal gradients generate internal stresses that propagate through the comet's structure like geological fault lines, creating weaknesses that can suddenly give way under the mounting pressure. Computer models of cometary nuclei suggest that objects like SWAN R2 likely contain numerous internal voids and fractures legacy damage from their violent formation in the early solar system and billions of years of exposure to cosmic radiation. These pre-existing weaknesses act as stress concentrators, similar to how a small crack in glass can suddenly propagate across an entire window when subjected to thermal shock. The sublimation process itself adds another destructive force. As water ice transitions directly from solid to vapor, it expands by a factor of nearly 500, creating enormous internal pressures. If this expansion cannot be accommodated by material flowing to the surface, It can literally blow the comet apart from within. The process is analogous to what happens when water pipes burst in winter, but on a scale measured in cubic kilometers rather than cubic inches. Rotational stress compounds these thermal effects in potentially catastrophic ways. As material streams away from specific regions of the nucleus, it creates torques that can spin up the comet's rotation. Most comets rotate with periods measured in hours or days, but as mass is lost asymmetrically, conservation of angular momentum can gradually increase the rotation rate until centrifugal forces exceed the comet EU's gravitational binding strength. For an object the size of SWAN R2, the critical rotation period, the point at which centrifugal force equals gravity, is likely just a few hours. If outgassing events cause the rotation to accelerate beyond this limit, the comet would literally fly apart as pieces of its surface are flung into space at velocities of several meters per second. The Shoemaker-Levy 9 event provides a sobering preview of what SWAN R2 fragmentation might look like. When that comet broke apart, it created a string of fragments ranging from a few hundred meters to several kilometers across, each following a slightly different trajectory as they approached Jupiter. The impacts, spread across 6 days in July 1994, created fireballs larger than Earth and left dark scars in Jupiter's atmosphere that persisted for months. If SWAN R2 were to fragment in a similar manner, the resulting debris stream could pose threats that persist for decades or centuries. Unlike a single intact comet that presents a point target moving along a predictable path, a fragmented comet becomes a distributed threat. Multiple objects of various sizes following related but distinct trajectories that could encounter Earth at different times and from different directions. The timing of any fragmentation event would be crucial in determining the nature of the threat. A breakup occurring near aphelion, at the comet's most distant point from the Sun, would spread the fragments over a relatively large volume of space, reducing the probability of any individual piece threatening Earth. The low velocities involved in such a distant fragmentation would also limit how far apart the fragments could drift over time. But fragmentation near perihelion presents a far more dangerous scenario. The high velocities involved, SWAN R2 will be moving at roughly 40 kilometers per second at its closest approach to the Sun, mean that even small velocity differences between fragments can lead to dramatically different trajectories. A fragment gaining just 1 kilometer per second relative to the main body could end up on a completely different orbit, potentially one that intersects Earth's path at some future date. The size distribution of fragments from a cometary breakup follows patterns that maximize the threat potential. Rather than creating a few large pieces or many tiny ones, fragmentation events typically produce a power law distribution with numerous medium-sized fragments, objects large enough to survive atmospheric entry and cause regional devastation, but small enough to be difficult to detect and track individually. Modern simulations of SWAN R2 fragmentation scenarios reveal disturbing possibilities. A major breakup occurring during the comet's current perihelion passage could create dozens of kilometer-sized fragments, each potentially capable of causing continent-scale destruction if it were to impact Earth. These fragments would initially follow trajectories similar to the parent comet, but gravitational perturbations from the planets would gradually spread them out over time. The debris stream from a fragmented SWAN R2 could persist as a hazard for thousands of years. Each time the fragment swarm completes an orbit around the Sun, individual pieces would return to the inner solar system at slightly different times and along slightly different paths. This creates multiple opportunities for Earth encounters, turning a single 24-year threat cycle into a sustained bombardment scenario extending across multiple millennia. Tidal fragmentation represents another mechanism by which SWAN R2 could break apart, though this would require a much closer approach to a massive body than currently predicted. If the comet were somehow deflected onto a trajectory that brought it within a few planetary radii of Earth or another planet, tidal forces could overcome the comet's gravitational binding and tear it apart. The resulting fragments would be spread along the comet's orbital path, creating a debris stream that Earth would encounter on subsequent orbits. The observational challenge of tracking fragmented comets adds another layer of danger to these scenarios. While a single intact comet presents a clear target for astronomical monitoring, dozens of fragments scattered across millions of kilometers of space strain the capabilities of even our most advanced detection systems. Small fragments might remain undetected until they're already approaching Earth, providing little warning time for any potential defensive measures. Historical precedent suggests that cometary fragmentation events are not rare occurrences. Beyond the famous Shoemaker-Levy 9 case, astronomers have observed the breakup of numerous comets, including Comet Linear in 2000, Comet Ison in 2013, and several others. These events demonstrate that even comets that appear structurally sound can suddenly disintegrate when subjected to the thermal and gravitational stresses of close solar approaches. The fragmentation of Comet 73 pp Schwarzmann-Wachmann in 2006 provides another instructive example. This comet broke into dozens of fragments that spread out along its orbital path, creating an extended debris stream that posed multiple encounter opportunities with Earth. While none of the fragments were large enough to cause global catastrophe, the event demonstrated how quickly a single object can become a distributed threat. Recent research has revealed that many comets may be rubble piles, loose aggregations of smaller pieces that are only weakly bound together. If SWAN R2 has this structure, it might be particularly susceptible to fragmentation as thermal expansion and outgassing disrupt the delicate balance of forces holding it together. Such objects can disintegrate with little warning, transforming from apparently stable comets into clouds of debris in a matter of hours. The gravitational environment that a fragmenting comet encounters can dramatically influence the evolution of the resulting debris stream. Fragments created near Jupiter's orbit would be subject to the giant planet's powerful gravitational field, which could scatter them onto widely different trajectories. Some pieces might be ejected from the solar system entirely, while others could be deflected onto shorter period orbits that bring them back to the inner solar system much sooner than the original comet. Perhaps most unsettling is the realization that we currently have no reliable method for predicting when or if a comet like SWAN R2 might fragment. While we can identify stress factors and calculate theoretical failure modes, the actual breakup of a comet often occurs suddenly and without clear warning signs. A comet that appears perfectly stable one day might be a scattered debris field the next. The cascade effects of fragmentation could extend far beyond the immediate creation of multiple threats. The dust and gas released during a major breakup event could alter the orbits of the resulting fragments through radiation pressure and gas drag effects. These subtle forces, acting over thousands of years, could gradually disperse the debris stream throughout the inner solar system, creating a long-term enhancement in the background impact rate. As we continue to monitor SWAN R2's approach and behavior, the possibility of fragmentation remains one of the most unpredictable and potentially catastrophic variables in our assessment of the comet's threat potential. The transformation of a single massive object into dozens of smaller but still dangerous fragments would fundamentally change the nature of the cosmic threat we face, turning a manageable single-point hazard into a complex distributed problem that could challenge human civilization for generations to come. The mathematics of fragmentation operate according to principles of chaos theory, where small changes in initial conditions can lead to vastly different outcomes. In the case of SWAN R2, the difference between a stable passage and catastrophic breakup might come down to the precise timing of a thermal stress event or the exact angle of a gas jet. factors that remain beyond our current ability to predict or control. The precise mathematics of orbital mechanics. There exist regions of space so small they could fit within a city block, yet so consequential that passing through one could doom an entire planet. These gravitational keyholes represent the cosmic equivalent of threading a needle. Zones where a slight deflection during one orbital passage sets up a catastrophic collision during the next. As SWAN R2 approaches Earth's neighborhood, we must confront the terrifying possibility that this ancient wanderer might pass through one of these invisible gateways to destruction. The concept of gravitational keyholes emerged from studies of asteroid 99942 Apophis, an object that will pass uncomfortably close to Earth in 2029. Astronomers discovered that if Apophis passes through a specific region of space, just 600 meters wide during its 2029 encounter, Earth's gravity would precisely deflect it onto a collision course for its return in 2036. This narrow corridor of doom demonstrates how gravitational encounters in that appear perfectly safe can actually be setting up future catastrophes. For SWAN R2, similar keyholes exist throughout the three-dimensional space surrounding Earth. These invisible corridors are defined by complex gravitational mathematics that take into account the comet's velocity, trajectory, and the precise timing of its closest approach to our planet. Computer simulations reveal dozens of potential keyhole regions, each corresponding to different impact scenarios on the comet's next orbital return in approximately 22,554 years. The physics governing these gravitational keyholes operates on principles that seem almost maliciously designed to maximize long-term risk. When SWAN R2 passes through Earth's gravitational field, our planet's gravity acts like an invisible hand, slightly bending the comet's trajectory. For most paths through this gravitational field, the deflection simply shifts the comet's orbit by amounts that remain safely distant from Earth during future passages. But certain trajectories create what mathematicians call resonant returns. Orbital configurations where the deflected comet returns to Earth's vicinity at precisely the wrong time. The most dangerous keyholes correspond to deflections that place SWAN R2 into orbital periods that are simple fractions of Earth's orbital period, such as 1.1, 2.1, or 3.2 ratios. These resonant configurations maximize the probability that future encounters will occur when Earth occupies the same region of space. The size and location of these gravitational keyholes depend critically on SWAN R2's exact velocity and trajectory during its current approach. Small uncertainties in our observations of the comet's position and motion translate into significant uncertainties in the precise boundaries of dangerous regions. Current measurement errors of just a few meters in position or millimeters per second in velocity could shift keyhole locations by thousands of kilometers. What makes these keyholes particularly insidious is their relationship to the comet's physical properties and behavior. Non-gravitational forces from outgassing jets can nudge SWAN R2's trajectory by just the amount needed to thread one of these cosmic needles. An outburst that seems trivial in astronomical terms, perhaps altering the comet's velocity by just a few meters per second, could be precisely the perturbation needed to guide it through a gravitational keyhole. The temporal aspect of keyhole encounters adds another layer of complexity to impact risk assessment. Unlike direct collision threats that unfold over months or years, keyhole scenarios operate on multi-decadal timescales that exceed the planning horizons of human institutions. A keyhole passage during SWAN R2's current approach would set up a collision threat for the year 47,579, a time frame so distant that it challenges our ability to maintain institutional memory or continuity of purpose. Modern supercomputer simulations have mapped the gravitational keyhole structure around Earth with unprecedented precision, revealing a complex three-dimensional maze of dangerous and safe zones. These computational models incorporate not just Earth's gravity, but also the perturbing influences of the Moon, Sun, and other planets that can subtly shift keyhole locations over time. The results of these simulations are sobering. For an object with SWAN R2's orbital characteristics, dozens of significant keyholes exist within the comet's encounter geometry. Some correspond to direct impact scenarios on the next return, while others set up multi-orbit chains where the comet passes through additional keyholes during subsequent approaches, gradually spiraling inward toward an eventual collision. The most dangerous keyholes are those that create what astronomers call impact certainty. Deflections that guarantee a collision during the next orbital return, regardless of other perturbations. These represent points of no return in the truest sense, where passage through a specific region of space makes future catastrophe mathematically inevitable. Lunar gravity complicates the keyhole structure around Earth, creating time-variable corridors that shift location depending on the Moon's orbital position during SWAN R2's closest approach. This gravitational choreography means that keyholes that might be safely avoided during one lunar phase could become unavoidable threats just days later as the Moon moves through its orbit. The three-dimensional nature of these keyholes makes them particularly difficult to visualize and understand. Unlike simple two-dimensional concepts, gravitational keyholes exist as complex volumes in space that can have irregular shapes and multiple disconnected regions. A comet might avoid one dangerous zone only to encounter another keyhole corridor just kilometers away. Recent advances in chaos theory have revealed that keyhole structures around planetary bodies exhibit fractal properties, self-similar patterns that repeat at different scales. This means that large keyholes often contain smaller sub-keyholes within them, creating nested structures where different deflection amounts lead to impacts at different future times. The mathematics become so complex that even supercomputers can only sample a fraction of the possible scenarios. The sensitivity of keyhole locations to initial conditions exemplifies the profound unpredictability inherent in cosmic mechanics. Two comets with trajectories differing by less than the width of a city block could have completely different keyhole structures, with one facing dozens of dangerous zones, while the other encounters none at all. For SWAN R2, the uncertainty in current trajectory measurements creates what astronomers call keyhole probability clouds. Fuzzy regions where dangerous corridors might exist but cannot be precisely defined with current observational data. These probability distributions reveal that while we can identify general areas of concern, the exact locations of the most dangerous keyholes remain tantalizingly uncertain. The discovery of gravitational keyholes has fundamentally changed how astronomers assess long-term impact risks. Traditional approaches focused on calculating direct collision probabilities, but keyhole analysis reveals that gravitational deflections can create delayed action threats that don't manifest for decades or centuries after the initial encounter. This temporal disconnect between cause and effect creates profound challenges for planetary defense planning. Deflecting an asteroid or comet away from a direct impact might inadvertently guide it through a gravitational keyhole, transforming an immediate threat into a future catastrophe. Such scenarios require defense strategies that consider not just the current encounter, but all possible future consequences of intervention. The study of historical comet orbits reveals several cases where gravitational keyholes may have played a role in creating dangerous encounters. Some periodic comets follow orbits that suggest they may have passed through keyhole regions during previous approaches to Earth or other planets, gradually evolving from safe periodic visitors into potential impactors. The mathematical tools used to analyze keyhole structures push the boundaries of computational astronomy. Monte Carlo simulations must run millions of trajectory integrations to map out the complete probability space, while chaos theory algorithms search for the sensitive dependence on initial conditions that characterizes keyhole regions. Perhaps most disturbing is the realization that keyhole effects operate as cosmic amplifiers, transforming tiny measurement uncertainties into enormous future risks. The gravitational deflection that occurs during a keyhole passage can amplify small initial uncertainties by factors of millions or billions, making long-term predictions fundamentally unreliable. The existence of gravitational keyholes around Earth means that every close approach by a comet or asteroid must be evaluated not just for immediate impact risk, but for the possibility of setting up future catastrophic encounters. This butterfly effect in orbital mechanics demonstrates how a seemingly harmless flyby can plant the seeds of destruction that won't germinate for thousands of years. As SWAN R2 continues its approach toward Earth's gravitational neighborhood, astronomers are working frantically to refine their measurements of its trajectory and identify any potential keyhole passages. The race against time isn't just about predicting this comet's immediate behavior, but about determining whether its current passage might be setting up a cosmic time bomb for future generations. The gravitational keyholes surrounding Earth represent more than just mathematical curiosities. They're tangible reminders that in the cosmic arena, the distinction between salvation and catastrophe can be measured in meters. As SWAN R2 navigates through this invisible maze of gravitational corridors, it carries with it the potential to either pass harmlessly into the outer darkness or to thread one of these cosmic needles and seal Earth's fate for a collision still more than 20,000 years in the future. But even if SWAN R2 successfully avoids all gravitational keyholes during its current passage, other mechanisms exist by which this ancient visitor could still pose a threat to our planet. The complex interplay of factors that determine impact risk extends far beyond simple gravitational deflections. The most insidious aspect of cosmic catastrophe is not the immediate destruction, but the slow starvation that follows when the sun disappears behind a veil of dust and debris. Impact winter represents the delayed revenge of cosmic collision, a global climate catastrophe that can persist for months or years after the initial impact, turning a regional disaster into a planet-wide extinction event. As we contemplate the worst-case scenarios for SWAN R2, we must confront the terrifying reality that even a near miss could trigger climatic changes severe enough to threaten the foundations of human civilization. The physics of impact winter begins with the simple but devastating principle that blocking sunlight can kill more effectively than any explosion. When a large object like SWAN R2 strikes Earth's surface, it doesn't just create a crater. It launches enormous quantities of pulverized rock, soil, and debris into the atmosphere. This material, heated to thousands of degrees by the impact, rises high into the stratosphere, where it can remain suspended for months or years, creating a planet-wide shroud that blocks incoming solar radiation. Computer models of SWAN R2 impact scenarios paint a picture of almost inconceivable destruction. The comet's estimated mass of several trillion kilograms, combined with impact velocities that could exceed 60 kilometers per second, would release energy equivalent to billions of nuclear weapons. The immediate fireball would vaporize everything within hundreds of kilometers of the impact site. But this local destruction would be dwarfed by the global consequences of the atmospheric debris. The amount of material ejected into the atmosphere scales dramatically with impact energy. For an object the size of SWAN R2, impact models suggest that hundreds of billions of tons of pulverized Earth could be launched into the stratosphere. This debris cloud would rapidly spread around the globe, carried by high-altitude winds and atmospheric circulation patterns that would distribute the destruction to every corner of the planet within weeks. The optical depth of this debris cloud, a measure of how effectively it blocks sunlight, would likely exceed the threshold for severe global cooling. Even if only a small fraction of incoming solar radiation were blocked, the cumulative effect over months could reduce global temperatures by 10–15 degrees Celsius. Such cooling would be sufficient to trigger widespread crop failures and ecosystem collapse across the planet. The Chicxulub impact 66 million years ago provides our best natural experiment in impact winter dynamics. Geological evidence from the Cretaceous-Paleogene boundary reveals layers of soot and shocked minerals that tell the story of a world plunged into darkness. Core samples from around the globe show evidence of rapid temperature drops, acid rain, and ecosystem collapse that persisted for thousands of years after the initial impact. Modern climate models, calibrated against this geological evidence, suggest that the Chicxulub impact may have reduced global temperatures by 20–30 degrees Celsius for several months, with cooling effects persisting for years or decades. The resulting nuclear winter effect eliminated photosynthesis across large regions of the planet, causing food webs to collapse from the bottom up. For SWAN R2, the composition of the impactor adds additional layers of complexity to impact winter scenarios. Unlike rocky asteroids, comets contain significant amounts of volatile materials: water, carbon dioxide, methane, and various organic compounds that could contribute to atmospheric chemistry changes beyond simple light-blocking effects. The vaporization of SWAN R2's icy components during impact would inject enormous quantities of water vapor into the stratosphere. While water vapor is normally a greenhouse gas that warms the planet, its effects at stratospheric altitudes are more complex. High-altitude water vapor can form persistent clouds that both reflect incoming sunlight and trap outgoing thermal radiation, creating competing effects that could either amplify or moderate the cooling from solid debris. The carbon dioxide locked within SWAN R2's nucleus presents another wild card in impact winter calculations. A comet impact could release millions of tons of CO2 directly into the atmosphere, potentially creating long-term warming effects that might persist after the dust settles. This could lead to a biphasic climate catastrophe. Severe cooling during the first months or years, followed by enhanced greenhouse warming that persists for decades or centuries. Organic compounds in comets introduce the possibility of atmospheric chemistry changes that could have global biological consequences. The shock heating of organic materials during impact could create toxic compounds that rain down across the planet, poisoning water supplies and contaminating agricultural land. Some models suggest that the atmospheric chemistry changes alone could be sufficient to trigger mass extinctions even without severe cooling. The geographic location of an SWAN R2 impact would significantly influence the severity and duration of impact winter effects. An ocean impact might initially seem less devastating than a land impact, but it could actually be worse for global climate. Ocean impacts vaporize enormous quantities of seawater, creating massive steam clouds that can persist in the atmosphere for extended periods. The salt content of vaporized seawater could also create chemical reactions in the stratosphere that produce acid rain on a global scale. Land impacts create different but equally severe problems. Impact into sedimentary rocks could release vast quantities of sulfur compounds that form aerosols in the stratosphere. These sulfur particles are particularly effective at scattering sunlight and could persist in the atmosphere much longer than simple dust particles. Impact into carbonate rocks could release enormous quantities of carbon dioxide, while impact into organic-rich sediments could produce toxic gases and soot. The seasonal timing of an impact would also influence its global effects. An impact occurring during Northern Hemisphere winter could trigger cooling feedback loops that prevent normal spring warming, potentially locking large regions into extended winter conditions. Conversely, An impact during peak growing season could maximize agricultural damage by occurring when crops are most vulnerable to temperature and light changes. Modern agricultural systems would be particularly vulnerable to impact winter scenarios. Industrial agriculture depends on consistent growing seasons, stable temperatures, and predictable precipitation patterns. Even modest cooling or light reduction could trigger widespread crop failures across the globe's major agricultural regions. The resulting food shortages could kill more people than the impact itself through famine, social unrest, and the collapse of international trade systems. The vulnerability of modern technology adds another dimension to impact winter catastrophe. Atmospheric electrical effects from the impact could disrupt electronic systems across the planet. The electromagnetic pulse generated by the initial impact, combined with ongoing electrical activity in the debris-laden atmosphere, could damage satellites, power grids, and communication systems just when they're most needed for coordinating recovery efforts. Nuclear winter research from the Cold War era provides additional insights into how impact winter might unfold. Computer models developed to study the climatic effects of nuclear war reveal that even relatively modest amounts of atmospheric debris can trigger severe cooling effects. A nuclear exchange involving just a small fraction of the world's arsenals could produce cooling effects lasting months or years. The social and economic consequences of impact winter could persist long after the atmospheric effects subside. The collapse of agricultural systems would trigger massive population migrations as people fled affected regions in search of food and habitable conditions. International conflicts could erupt over remaining resources, potentially leading to wars that cause additional devastation beyond the initial impact. Recovery from severe impact winter could take decades or centuries. Even after the atmosphere clears and normal temperatures return, damaged ecosystems would need time to recover. Soil contaminated by acid rain and toxic fallout might remain unproductive for years. The extinction of key species could trigger ecological cascades that prevent ecosystem recovery for generations. Recent research has revealed that the recovery from the Chicxulub impact was highly uneven across different regions and ecosystems. Some areas recovered relatively quickly, while others remained devastated for millions of years. The pattern of recovery depended on factors like geographic location, local geology, and pre-impact ecosystem structure. The possibility of multiple impact winter events from a fragmented SWAN R2 introduces scenarios even more catastrophic than a single large impact. If the comet breaks apart and delivers multiple impacts over days, weeks, or years, each impact could refresh the atmospheric debris load just as it begins to settle. This could create sustained impact winter conditions lasting far longer than those produced by a single event. Paleontological evidence suggests that some past extinction events may have involved multiple impacts or sustained periods of environmental stress. The Permian-Triassic extinction 252 million years ago, which eliminated over 90% of marine species, appears to have involved multiple environmental catastrophes occurring over hundreds of thousands of years. Perhaps most sobering is the realization that modern civilization has no effective defenses against impact winter once it begins. Unlike direct impact effects that might be mitigated through early warning and evacuation, impact winter affects the entire planet simultaneously. There's no safe place to retreat, no unaffected region that could serve as a refuge for displaced populations. The global nature of impact winter also means that international cooperation would be essential for survival. Yet the stress of the catastrophe could just as easily trigger conflicts that make cooperation impossible. History shows that societies under extreme stress often fragment and turn on each other rather than working together for mutual survival. As we track SWAN R2's approach and contemplate these worst-case scenarios, we're forced to confront the humbling reality that a single cosmic visitor carries within its ancient structure the power to transform our world in ways that dwarf any catastrophe in recorded human history. The beautiful tale streaming behind this cosmic wanderer as it approaches the sun isn't just a spectacular light show. It's a visible reminder of the forces that could plunge our entire planet into darkness. But understanding the threats posed by objects like SWAN R2 is only the first step. The question that haunts our exploration of these cosmic catastrophes is whether humanity possesses the technology and wisdom to defend itself against such threats, or whether we remain as vulnerable as the dinosaurs who watched their world end 66 million years ago. The cosmic threat bearing down on our planet moves with the inexorable patience of celestial mechanics. Yet our defenses against such visitors remain surprisingly fragile and incomplete. As SWAN R2 continues its approach through our solar system, we must confront an uncomfortable question. If this ancient wanderer were actually on a collision course with Earth, would we possess the technology, coordination, and time necessary to prevent the end of civilization as we know it? The current state of planetary defense represents humanity's first serious attempt to shield itself from cosmic catastrophe, but the scope of the challenge dwarfs our current capabilities. NASA's Planetary Defense Coordination Office, established in 2016, monitors potentially hazardous objects and coordinates international responses to cosmic threats. However, this office operates with a budget smaller than that of a major Hollywood movie, and its mandate covers threats from space objects that could range from city killers to civilization enders. Our detection capabilities, while impressive by historical standards, remain woefully inadequate for threats like SWAN R2. Ground-based survey telescopes can identify large asteroids and comets years or decades before potential impacts, but they're blind to objects approaching from the direction of the sun. Exactly how SWAN R2 remained hidden for months before its discovery. A comet on a true collision course could theoretically remain undetected until just weeks or months before impact. The Catalina Sky Survey, Linear, NEOWISE, and other detection programs have identified over 90% of near-Earth asteroids larger than 1 kilometer in diameter. This might sound reassuring until we realize that SWAN R2, despite being potentially much larger, was discovered only by chance and only 1 day before its closest approach to the Sun. Long-period comets from the Oort cloud represent a particularly challenging detection problem because they approach from unpredictable directions and can remain dormant until very close to the Sun. Space-based detection systems offer some advantages over ground-based telescopes, but they come with enormous costs and technical challenges. The proposed NEO Surveyor mission, if fully funded and successfully deployed, would improve our ability to detect threatening objects approaching from the Sun's direction. However, even this advanced system would provide only months or years of warning for fast-moving comets, potentially insufficient time for effective defensive measures. The deflection technologies currently available to humanity fall broadly into 2 categories: kinetic impactors and gravity tractors. NASA's successful DART mission demonstrated that we can alter the trajectory of a small asteroid through kinetic impact, but scaling this technology up to objects the size of SWAN R2 presents enormous challenges. The energy required to significantly deflect a multi-kilometer comet exceeds the capabilities of any existing or planned spacecraft. Nuclear deflection systems, while politically and environmentally controversial, represent our most powerful option for dealing with large cosmic threats. A nuclear device detonated near or on the surface of an incoming comet could vaporize enough material to create a reaction thrust capable of altering its trajectory. However, nuclear deflection requires precise timing, accurate targeting, and sophisticated modeling of how the explosion would affect the comet's structure and motion. The complexity of nuclear deflection multiplies when dealing with comets rather than asteroids. The volatile-rich composition of objects like SWAN R2 means that nuclear heating could trigger massive outgassing events that either amplify the deflection effect or create unpredictable trajectory changes. Worse yet, nuclear bombardment could fragment the comet, transforming a single large threat into multiple smaller but still dangerous projectiles. International coordination represents perhaps the greatest challenge in planetary defense scenarios. Deflecting a cosmic threat requires not just advanced technology, but also unprecedented global cooperation. Treaties governing the use of nuclear weapons in space, competing national interests, and the sheer difficulty of coordinating complex operations across multiple countries and space agencies could fatally delay defensive efforts. The timeline for planetary defense operations compounds these coordination challenges. Unlike terrestrial threats that might develop over months or years, cosmic impacts can transition from distant possibilities to imminent catastrophes in just weeks or days. For long-period comets like SWAN R2, the entire window from detection to potential impact might be shorter than the time required to design, build, and launch an effective defensive mission. Cost considerations add another sobering dimension to planetary defense planning. A comprehensive defense system capable of handling threats like SWAN R2 would require investments measured in hundreds of billions of dollars, resources that must compete with immediate social, economic, and political priorities. The challenge of maintaining such expensive systems over decades, waiting for threats that might never materialize, tests the limits of political sustainability. The fragmentation scenario poses particularly difficult challenges for planetary defense. If SWAN R2 were to break apart naturally or as a result of defensive intervention, the resulting debris stream could contain dozens of fragments large enough to cause regional devastation. Tracking and potentially deflecting multiple objects simultaneously would overwhelm current defensive capabilities and require defensive technologies that don't yet exist. Advanced propulsion systems offer theoretical solutions to some planetary defense challenges, but they remain far from practical implementation. Solar sails, ion drives, and even more exotic concepts like fusion rockets could potentially deliver the sustained thrust needed to deflect large comets over extended periods. However, these technologies are decades away from the reliability and scale needed for planetary defense applications. The warning time problem represents a fundamental limitation of current planetary defense concepts. Most deflection strategies require years or decades of advance warning to be effective. Yet comets like SWAN R2 might provide only months of notice. This temporal mismatch between detection capabilities and defensive requirements creates scenarios where we might identify a cosmic threat but remain powerless to prevent it. Recent research into rapid response systems has explored concepts like interceptor fleets, networks of pre-positioned spacecraft that could respond to newly detected threats within months rather than years. However, the cost and complexity of maintaining such systems in space, combined with the uncertainty about where threats might emerge, makes this approach economically prohibitive with current technology. The psychological and social dimensions of planetary defense present challenges that extend beyond technology and coordination. Public reaction to cosmic threats can range from panic and social disruption to denial and inaction. Managing information about potential impacts requires balancing the need for public preparedness with the risk of triggering social collapse before any impact occurs. Historical precedent for managing existential threats offers mixed guidance for planetary defense scenarios. The Cold War demonstrated that humans can maintain expensive defensive systems for decades while living under the shadow of potential catastrophe. However, it also revealed how the stress of existential threats can distort decision-making and trigger conflicts that create additional dangers. The role of private space companies in planetary defense remains largely untested, but potentially crucial. Companies like SpaceX, Blue Origin, and others possess launch capabilities and technical expertise that could be essential for rapid response to cosmic threats. However, integrating private capabilities into government-led defense efforts requires new models of public-private cooperation that have yet to be fully developed. Scientific uncertainty compounds every aspect of planetary defense planning. Our understanding of comet structure, composition, and behavior remains incomplete. The moral dimensions of planetary defense create ethical dilemmas that have no clear solutions. If defensive efforts succeed in deflecting a comet away from Earth, there's always a possibility that the altered trajectory could threaten other worlds or future human settlements in space. The decision to fragment a threatening comet could protect Earth while creating long-term hazards for space exploration and development. Regional defense systems offer a more modest, but potentially achievable approach to cosmic threats. Rather than attempting to deflect entire comets, regional systems might focus on protecting specific populated areas from fragment impacts through advanced warning systems, blast shelters, or even local interceptor systems. While this approach couldn't prevent global catastrophes like impact winter, it could reduce casualties from smaller-scale impacts. The insurance and economic implications of planetary defense extend far beyond government budgets. Global economic systems, insurance markets, and financial institutions would all be affected by credible cosmic threats. The mere possibility of impact could trigger economic disruptions that cause more immediate harm than the cosmic threat itself. As we contemplate SWAN R2's passage through our cosmic neighborhood, we're forced to acknowledge that humanity's defenses against cosmic catastrophe remain largely theoretical. We possess the basic technologies needed for planetary defense, but we lack the scale, coordination, and rapid response capabilities that would be required to handle a true existential threat from space. The beautiful comet streaming across our skies serves as both an inspiration and a warning. A reminder that the universe contains forces vastly more powerful than human technology, operating on timescales that dwarf political planning horizons. Whether we can develop the capabilities needed to defend our world against the next cosmic visitor may depend less on our technological prowess than on our ability to transcend the short-term thinking and narrow interests that have historically divided our species. The sobering reality is that if SWAN R2 were actually on a collision course with Earth, our current planetary defense capabilities would likely prove inadequate to prevent catastrophe. We might detect the threat months or years in advance. We might launch desperate missions to deflect or fragment the comet. But the physics of moving mountain-sized objects traveling at cosmic velocities remains beyond our current reach. This doesn't mean that planetary defense is hopeless, but it does underscore the urgency of developing more robust capabilities before the next cosmic threat emerges from the depths of space. Every year we delay implementing comprehensive detection and deflection systems is another year we remain vulnerable to the kind of catastrophic impact that has repeatedly reshaped life on Earth throughout geological history. The technologies needed for effective planetary defense exist in theory and, in some cases, in early practical forms. What's missing is the sustained political will, international cooperation, and financial commitment needed to transform these concepts into operational systems capable of protecting our entire planet. As SWAN R2 fades back into the cosmic darkness, it leaves behind a critical question about whether humanity will choose to remain vulnerable to cosmic catastrophe or finally take the steps necessary to defend our world against threats from the infinite night. There's something uniquely terrifying about threats that emerge from the infinite darkness above our heads. Unlike earthly disasters that feel comprehensible and manageable, cosmic dangers tap into primal fears that have haunted humanity since our ancestors first looked up at the night sky and wondered what lurked in the vast emptiness between the stars. As SWAN R2 continues its ancient journey through our solar system, its mere presence raises profound questions about how human civilization might psychologically survive not just cosmic impact, but the sustained psychological stress of living under such existential threats. The discovery and tracking of potentially hazardous cosmic objects like SWAN R2 creates a new category of collective anxiety that has no historical precedent. Previous generations lived under the shadow of immediate threats: war, disease, natural disaster, but they were spared the knowledge that mountain-sized projectiles travel through space on trajectories that could intersect Earth at cosmic velocities. The burden of this knowledge weighs differently on a species that has only recently developed the ability to detect such threats, decades or centuries before potential impacts. Modern society's relationship with cosmic threats reflects a fundamental disconnect between the timescales of human psychology and astronomical events. Our brains evolved to deal with immediate dangers that could be fought, fled from, or hidden from until they passed. The concept of a threat that approaches over decades, that cannot be negotiated with or avoided through individual action, challenges the basic assumptions that underlie human stress response systems. The psychological literature on existential threats provides some guidance for understanding how people might react to confirmed cosmic dangers. Studies of populations living under nuclear threat during the Cold War revealed a complex spectrum of responses ranging from denial and magical thinking to hypervigilance and premature despair. Some individuals developed sophisticated coping mechanisms that allowed them to function normally despite living under the shadow of potential annihilation, while others experienced chronic anxiety that interfered with basic life functions. The global nature of cosmic threats creates psychological dynamics that differ fundamentally from localized disasters. When a hurricane threatens a specific region, people can evacuate or prepare locally, while the rest of the world provides support and refuge. But a cosmic impact represents a planetary threat that offers no safe harbor, no unaffected population to provide assistance. The universality of the danger could either unite humanity in common cause or trigger competitive responses as groups prioritize their own survival over collective action. Religious and philosophical frameworks would likely play crucial roles in how different populations interpret and respond to cosmic threats. Some belief systems might frame cosmic impacts as divine judgment or cosmic destiny, leading to fatalistic acceptance or frenzied attempts at spiritual intervention. Others might view such threats as challenges to be overcome through human ingenuity and cooperation, potentially galvanizing technological and social progress. The role of media and communication in shaping public response to cosmic threats cannot be understated. The same information that allows scientists to track and analyze objects like SWAN R2 also creates opportunities for sensationalism, misinformation, and panic. Social media platforms optimized for engagement could amplify fears and conspiracy theories about cosmic threats, potentially creating social disruption that exceeds the actual danger from the cosmic object itself. Historical analogies provide limited guidance for understanding societal response to cosmic threats because no previous generation has faced the combination of advanced detection capabilities and sustained awareness of potential impacts. The closest historical parallels might be found in societies that developed apocalyptic beliefs around astronomical events, but these typically involved supernatural rather than physical explanations for cosmic dangers. The economic and social implications of sustained cosmic threat awareness could be as disruptive as the impacts themselves. If credible threats were detected decades in advance, long-term planning for everything from infrastructure investment to population growth could be affected. Why build for the future if that future might be destroyed by cosmic impact? Why have children who might face catastrophic events beyond human control? Children and adolescents might be particularly vulnerable to the psychological effects of cosmic threat awareness. Developmental psychology suggests that exposure to existential threats during formative years can have lasting effects on personality development, risk perception, and life planning. A generation raised with knowledge of specific cosmic threats approaching over their lifetimes might develop fundamentally different attitudes toward long-term thinking and future planning. The scientific community faces unique psychological challenges in communicating about cosmic threats. Astronomers and planetary scientists must balance the need for public awareness with the risk of triggering panic or despair. The precise mathematical language of orbital mechanics and impact probability doesn't translate easily into public communication, creating opportunities for misunderstanding and misinterpretation. Professional psychological support systems would likely need to evolve to address cosmic threat anxiety. Traditional therapeutic approaches designed for manageable life stresses might prove inadequate for helping people cope with potential planetary catastrophe. New models of psychological intervention might need to incorporate existential philosophy, community support systems, and practical preparedness planning. The concept of cosmic anxiety represents a new category of mental health concern that could affect millions of people even if no actual impacts occur. The mere knowledge that potentially hazardous objects regularly pass close to Earth, combined with awareness that our detection and deflection capabilities remain limited, could create chronic stress conditions in susceptible individuals. Social cohesion could either strengthen or fragment under sustained cosmic threat. Shared existential danger has historically brought communities together, but it has also triggered competition for limited resources and triggered conflicts between groups with different survival strategies. The global scale of cosmic threats might overwhelm traditional social support mechanisms while creating new forms of international cooperation. The psychological timeline of cosmic threat response would likely follow predictable patterns identified in disaster psychology, but extended over much longer periods. Initial shock and disbelief might give way to bargaining and anger, followed by either acceptance and adaptation or depression and despair. However, the extended timescales involved in cosmic threats could trap populations in extended psychological limbo between hope and fear. Cultural differences in cosmic threat perception could create international tensions even if no actual impact occurs. Societies with different attitudes toward fate, technology, and collective action might respond very differently to the same threat information, potentially leading to conflicts over resource allocation or defensive strategies. The role of hope and agency in psychological survival becomes crucial when facing threats beyond individual control. Populations that believe they can influence their cosmic fate through technological development, international cooperation, or collective action might maintain better psychological health than those who view such threats as inevitable or divinely ordained. Educational systems would face the challenge of preparing citizens for cosmic realities without creating pervasive anxiety or despair. Teaching about cosmic threats requires balancing scientific accuracy with psychological wellness, helping people understand genuine risks without becoming paralyzed by fears they cannot directly address. The entertainment industry's portrayal of cosmic threats could significantly influence public psychological response to real dangers. Science fiction films and literature often dramatize cosmic impacts in ways that emphasize destruction and hopelessness rather than human agency and scientific solutions. These cultural narratives could shape expectations and responses when faced with actual cosmic threats. Mental health infrastructure might need significant expansion to address the psychological needs of populations living under sustained cosmic threat awareness. Current mental health systems are already strained by everyday psychological challenges. Adding cosmic existential anxiety to this burden could overwhelm available resources and create new categories of psychological casualty. The intergenerational aspects of cosmic threat psychology present particularly complex challenges. How do you explain to children that their world might end not through human action, but through cosmic accident? How do you maintain cultural traditions and long-term social institutions when faced with potential planetary catastrophe on astronomical timescales? Leadership psychology becomes crucial in cosmic threat scenarios because political and scientific leaders must maintain public confidence while honestly communicating about genuine dangers. The psychological qualities needed for effective leadership during sustained existential threats may differ significantly from those required for normal political or scientific leadership. As SWAN R2 continues its passage through our cosmic neighborhood, it serves as more than just a spectacular astronomical object. It's a psychological test case for how humanity might respond to confirmed cosmic threats. Even though this particular comet poses no direct danger, its discovery and tracking process reveals the complex psychological dynamics that would emerge if we faced a genuine existential threat from space. The beautiful tale streaming behind SWAN R2 as it approaches the Sun might inspire wonder and scientific curiosity, but it also reminds us that the universe contains forces capable of destroying everything humans have built and will ever build. Learning to live with this knowledge while maintaining psychological health and social cohesion may be one of the greatest challenges facing our technologically advanced but psychologically vulnerable species. Whether humanity can develop the psychological resilience needed to survive in a cosmos filled with potential threats may ultimately determine our long-term survival as much as our technological capabilities for detecting and deflecting dangerous objects. The cosmos tests not just our engineering skills, but our wisdom, courage, and ability to maintain hope in the face of forces beyond our complete control. As SWAN R2 begins its slow retreat back toward the outer darkness from which it came fading from telescopic view, as it moves beyond the warming influence of our Sun, we are left to contemplate what its passage has taught us about our place in a universe that operates according to scales and forces that dwarf human comprehension. The comet's departure marks not just the end of a spectacular celestial show, but the conclusion of a cosmic reminder that Earth exists in a dynamic, dangerous universe where mountain-sized projectiles regularly traverse the space between planets. The gradual dimming of SWAN R2's magnificent tail serves as a metaphor for how quickly cosmic threats can transform from immediate concerns to distant memories. Within months, this comet that captured global attention and sparked fears about worst-case scenarios will become invisible to all but the most powerful telescopes. Its 2.5-degree tail, once spanning 5 full moon diameters across our sky, will dissipate as the comet moves away from solar heating and returns to its dormant state. But the psychological and scientific legacy of SWAN R2's passage will persist long after the object itself fades from view. This comet has served as an unwitting ambassador from the outer solar system, carrying messages about cosmic timescales, orbital dynamics, and the ever-present possibility that our planet's future could be shaped by visitors from the vast darkness beyond Neptune's orbit. The scientific data gathered during SWAN R2's passage represents one of the most comprehensive studies of a long-period comet in human history. Spectroscopic observations have revealed details about its composition and origin. Orbital measurements have refined our understanding of how such objects evolve over time, and thermal observations have provided insights into the internal structure of these ancient ice mountains. This information will inform our understanding of cosmic threats for generations to come. Yet perhaps the most important lesson from SWAN R2's visit concerns not the comet itself, but our own capabilities and limitations in dealing with cosmic threats. The comet's discovery just one day before perihelion highlighted critical gaps in our detection systems. Its months-long concealment behind solar glare demonstrated how easily dangerous objects could approach undetected. Its unpredictable outgassing behavior reminded us that even when we detect cosmic visitors, predicting their exact behavior remains challenging. The worst-case scenarios we've explored tonight aren't science fiction. They're mathematical possibilities embedded in the complex gravitational dynamics that govern our solar system. While SWAN R2 posed no direct threat during its current passage, it belongs to a population of objects that includes potential planet killers following similar orbits through the outer reaches of our cosmic neighborhood. The sobering reality is that objects like SWAN R2 will continue to visit our inner solar system for as long as the sun shines. The Oort cloud contains trillions of icy bodies, any of which could be nudged onto dangerous trajectories by gravitational perturbations from passing stars or giant planets. The statistical certainty is that Earth will eventually face another major cosmic impact. The only questions are when and whether humanity will be prepared. Our exploration of impact physics, orbital mechanics, and planetary defense capabilities has revealed both reasons for hope and grounds for concern. The technologies needed to deflect cosmic threats exist in principle, and, in some cases, in early practical forms. International cooperation on space projects demonstrates that humanity can work together when faced with challenges that transcend national boundaries. Scientific understanding of cosmic threats continues to advance rapidly as detection systems improve and computational capabilities expand. Yet, significant gaps remain in our cosmic defense capabilities. Detection systems optimized for asteroids approaching from predictable directions struggle with comets that can appear from any point in the sky with little warning. The psychological dimensions of living with cosmic threats may prove as challenging as the technical aspects of planetary defense. Human societies have never before possessed both the knowledge to detect approaching cosmic dangers and the awareness that such threats could materialize with little warning. Learning to function psychologically while living under this knowledge represents an unprecedented challenge for our species. The economic implications of comprehensive planetary defense systems raise difficult questions about resource allocation and long-term planning. The costs of building detection networks and deflection capabilities sufficient to handle objects like SWAN R2 would rival those of major military programs. Yet the benefits would accrue to all humanity rather than specific nations. Creating sustainable funding mechanisms for such global public goods remains an unsolved challenge. Climate change adds another layer of complexity to long-term cosmic threat planning. The same international cooperation and sustained commitment needed for planetary defense are also required to address climate change. Yet both challenges operate on timescales that exceed normal political planning horizons. Balancing immediate environmental threats against potential cosmic dangers requires wisdom and foresight that human institutions have rarely demonstrated. The role of private space companies in planetary defense offers both opportunities and complications. Commercial space capabilities have advanced dramatically in recent years, potentially providing cost-effective solutions for detection and deflection missions. However, integrating private resources into planetary defense strategies requires new models of public-private cooperation and raises questions about how to coordinate commercial interests with global security needs. Technological advancement continues to offer new possibilities for cosmic threat mitigation. Advances in artificial intelligence could improve our ability to predict orbital evolution and identify dangerous objects. Improvements in propulsion systems could enable more effective deflection missions. Development of space-based manufacturing could allow construction of defensive systems that would be prohibitively expensive to launch from Earth. Yet technology alone cannot solve the cosmic threat challenge. The social, political, and psychological aspects of planetary defense may prove more difficult than the technical challenges. Building sustainable institutions capable of maintaining vigilance across decades or centuries, coordinating international responses to ambiguous threats, and maintaining public support for expensive defensive systems all require advances in human organization that parallel our technological capabilities. The educational implications of cosmic threat awareness extend far beyond astronomy and planetary science. Future generations will need to understand not just the technical aspects of cosmic dangers, but also the ethical, political, and psychological dimensions of living with existential threats. Preparing citizens for a cosmos filled with potential dangers while maintaining hope and agency represents a fundamental challenge for educational systems worldwide. The philosophical implications of cosmic threats challenge some of humanity's most basic assumptions about progress, control, and meaning. The possibility that human civilization could be ended not through human action, but through cosmic accident, forces us to confront questions about the ultimate purpose and value of human achievement. How do we find meaning in building for the future when that future could be destroyed by forces beyond our control? Religious and spiritual traditions offer various frameworks for understanding humanity's relationship with cosmic forces, but they were developed before we understood the true scale and nature of cosmic threats. Modern spiritual thinking must grapple with the reality that Earth exists in a universe where destruction can arrive from directions we cannot predict, on timescales we cannot control. The intergenerational ethics of cosmic threat preparation raise difficult questions about our obligations to future generations. Do we have a moral duty to spend resources now to protect against threats that might not materialize for thousands of years? How do we balance current needs against potential future catastrophes? What do we owe to descendants who might face cosmic dangers we can identify but cannot prevent? Cultural evolution may be required for humanity to successfully adapt to cosmic realities. Our psychological and social systems evolved for life in small groups facing immediate local threats. Adapting to existence in a cosmos filled with potential planet killers may require fundamental changes in how we think about risk, time, and collective action. The search for extraterrestrial intelligence takes on new dimensions when considered in the context of cosmic threats. If other technological civilizations exist in our galaxy, they presumably face similar challenges from cosmic impacts. The absence of detectable alien signals might reflect not the rarity of intelligence, but the difficulty of surviving in a universe filled with extinction-level threats. As SWAN R2 disappears into the outer darkness, it leaves behind a changed human perspective on our cosmic environment. We can no longer view space as an empty void punctuated by distant, harmless lights. Instead, we must acknowledge that we live in a dynamic, dangerous universe, where ancient wanderers regularly traverse the space between worlds, carrying within their structure the potential to reshape entire planets. The beautiful comet that graced our skies for a few brief months represents both an inspiration and a warning. It reminds us that the universe contains wonders beyond imagination, but also dangers beyond our current ability to fully comprehend or control. Whether humanity can develop the wisdom, technology, and cooperation needed to thrive in such a cosmos remains one of the great unanswered questions of our time. The sky has cleared, SWAN R2 has departed, and life continues much as it did before this cosmic visitor appeared in our telescopes. But something fundamental has changed in our understanding of our place in the universe. We now know with certainty that we live on a small world orbiting an ordinary star in a galaxy filled with objects that could end our civilization in an instant. This knowledge brings both humility and responsibility. humility before forces that dwarf human power, and operate on scales that challenge human comprehension. Responsibility to protect our world and our species against threats we are only beginning to understand. As we watch the skies and wait for the next cosmic visitor to emerge from the darkness, we carry the weight of being perhaps the only species in our local region of the galaxy capable of contemplating such threats, and possibly the only one capable of doing something about them. The cosmos continues its ancient dance, indifferent to human hopes and fears. But for the first time in Earth's history, one species has developed the ability to watch the sky with understanding to calculate the paths of cosmic wanderers and perhaps to defend itself against the dangers that travel between the stars. Whether we prove worthy of this capability may determine not just our survival, but our right to call ourselves a truly spacefaring civilization. Subscribe to continue exploring the universe's most profound mysteries and the challenges they present to our small but remarkable species.